Okay, now let's do something with, well, let's write down the equations of circular motion. Okay, now just always remember, if I have a circle, I have something moving in a circle this time, say maybe a car, moving in this direction. Just always remember, the centripetal force is towards, the centripetal force is always towards the center of the circle. Also, the instant velocity, is always on the tangent of the path. Okay, now, okay. Okay, now, before we introduce the equation, you need to learn those terminologies. Okay, capital T stands for period. Okay? Period means the time that took our object, to travel one round of the circle. Okay, a period. R will be the radius. Also, please copy this down in your book. Okay, v will be the velocity, but in circular motion equations we use them as a speed. Okay, the velocity is always changing. The magnitude doesn't change. Okay, so also f is known as frequency. Okay, it means how many revolutions per second. Okay, so if you have a circular motion goes if you have a circular motion goes 10 hertz, frequency is measured in hertz. Okay, means how many revolutions per second. Okay. If it's 10 hertz, it means it travels in a circle 10 times every second. Okay, also just remember, now frequency is basically 1 second divided by the period. Period is measured in seconds. Okay, so yep, that's the information. Okay, now let me write down the equations. Okay, the velocity, actually the speed, of an object under circular motion will be 2 pi r divided by t, the period. Or 2 pi r times the frequency. Okay, and yep, that's equation 1. Okay. But the most useful equation you're going to use will be the centripetal acceleration. Okay. The acceleration will be recalled as v squared divided by r. Okay. Now, since Newton told me the net force is ma, so your centripetal force will be m times the acceleration, mv squared divided by r. Okay, so please copy this down in your notes, and just remember you're going to use this one. You're going to use these two equations very often. Okay, here are some examples for uniformed circular motion. Okay, now what we're going to do first will be the uniform circular motion. It means the circular motion does not does not affected by gravity. Okay, we're going to do ununiformed circular motion later, but for now just stay with this. Okay, again we have a question, we have mass, and okay, now then the radius, okay, is horizontal, means it's uniformed circular motion. The magnitude of the centripetal force, okay, will be this. What's the speed? Okay, so let's use the equation, put the value in. Okay, use your calculator, rearrange it, use your calculator to find an answer for the speed. Okay, so it will be square root of you can do that in your calculator. Okay, now the next question. Okay, so the safe speed, okay, let's all right. Okay, yep. Now let's have a read the question. Okay, then read. Now what's happening? Well, you read that by yourself. Okay. Now what's happened is which arrows indicates the direction of net force. Okay. Now the direction of net force is the direction of acceleration. Okay. At point Q, which is always towards the center of the circle. A. Now let's go to the next question. Okay, now okay, now okay, now what's happening is we have a traffic. This suggests one way to make it safer for the trucks to be traveling around the curve at the recommended speed. Okay, now this is an explanation question. Okay, so if we go back to the equation, okay, you can use either of these equations. Okay, now if the speed is kept constant, okay, what we can do is acceleration is inversely proportional to the radius. Okay, what I can suggest is, okay, since it is inversely proportional to the radius, that means when radius increases, okay, if the radius increase, okay, now my acceleration would decrease. Okay. Similarly, acceleration increases, my radius I need to decrease my radius. Okay, so what's happening is, if I want to be safer, a good way is to increase the radius. Okay. If I increase the radius, the acceleration will be decreased force will be decreased.